tricking it into allowing us to write to some pages that we're normally not allowed to write to. There's the architecture section, which often has, of course, architecture-specific vulnerabilities. KVM has suffered a huge rash of vulnerabilities, even though it's now officially Red Hat's officially blessed virtualization software as opposed to Xen. And there's also been some interesting vulnerabilities in the 32-bit compatibility. Chris Evans had a neat one where you could evade any sort of system call auditing framework by, I think it was calling out to 32-bit syscalls from a 64-bit process, bypassing some of the protections there. There's character devices, there's file systems, both virtual file systems, a format of binaries like your L for A.out. There's network file systems, there's local file systems. There's network drivers like the SCTP that we talked about. The Wi-Fi framework of Mac 802.11 is a recent addition to the Linux kernel. So there's been a handful of remote denial of service attacks against the Wi-Fi framework. None of them exploitable for execution of code, but they were some null pointer dereferences remotely triggerable. And then, of course, you have your device drivers, which are come and go once in a while. The Mad Wi-Fi, the one that Julian wrote, and more recently there was a E1000 vulnerability that you could actually, there's both a local and remote one. The remote was a denial of service, but the local one you could actually write arbitrary data into the cards and VRAM, essentially creating a NIC rootkit, which I was expecting to see in those NIC rootkit presentations in CASSEC West, but apparently no one covered that one. And contrary to popular belief, or at least in academia, people think that these vulnerabilities or these flaws are most commonly in device drivers. And really they're not. The device drivers are maybe serious ones because they can potentially be remote, but there's a lot of complexity in the kernel that is not as part of a device driver. So we want to start with a recent example, something fresh. Maybe it was released a week ago or so. There's a vulnerability in the RiserFS file system where Riser has this sort of top-level private directory called RiserFS priv, and the files beneath this can be written by an unprivileged user. It fails to enforce the permissions that it's supposed to. And this is a virtual path, so even if you run RiserFS, you've probably never seen this path because it won't even show if you do a ls-a. This is used for internal file system usage. One of the main users of this virtual path is extended attribute support. So extended attributes can be used for many reasons. Essentially, it was designed to deal with some of the shortcomings of your standard Unix stat structures, where you have your A time, M time, C time. You have your permission bits and your owner bits. So they really wanted something that could be extended without having to change the interface between the kernel and user space via stat every time. So these are just named attributes that can have any name and any value. But the root cause here, or the root result, is that we can actually write extended attributes for arbitrary files on the RiserFS file system. So, how do we actually escalate our privileges by writing these arbitrary extended attributes? One key use, which may be interesting, is the POSIX file capabilities, which allow you to specify more fine-grained privileges than simply setting the setuid bit on a particular binary. So instead of having your ping as setuid, which ping's been audited pretty hard over the years, but there used to be a lot more vulnerabilities in these setuid programs. And now we can actually take away that setuid bit and just assign it one particular capability that's necessary. So ping, since it just opens up ICMP raw socket to send out these ICMP echo requests, can just have the capnet raw. And capnet raw allows it to open raw sockets and nothing else. So we can kind of limit the attack surface of our system and of our collection of setuid binaries by using these capabilities. And these capabilities are stored as extended attributes in the file system. So this mechanism that's actually used to protect the system and make it more secure, we're going to leverage for our own exploit. And one of the capabilities, cap setuid, and it sounds pretty good for a candidate way to escalate our privileges. So what we can do is compile our own shell and throw it in a certain path within the RiserFS file system and attempt to set the capability for that particular file. Now, one of the roadblocks we run into is we don't actually know the inode or the object ID of this shell we've created. The object ID is the internal identifier that RiserFS uses. It's equivalent to an inode. And this is necessary because we need to know what path to write in the RiserFS priv directory in order to put our capabilities in the correct place. So we do a little trick where we can just compile the shell, get a list of the directory entries of that directory, sort of a pre-snapshot. We can set a dummy extended attribute as an unprivileged user, and then get another directory listing of that directory and see the change that has happened, and notice that the new entry in that is the inode of our shell. So we're going to go ahead and do a quick and hopefully painless demo against a fully patched Ubuntu system. Notice this isn't in a VM or anything. I'm actually exploiting my laptop, which is still vulnerable to this this attack. But it's a quick Python script. It's maybe like 50 lines. Not a big deal. Latest kernel. We can see that we're an unprivileged user, and we run our stuff, and we are now root on our system. And to celebrate, we have a ASCII animated volcano, which previously when we were talking in here, we were trying to Google for ASCII volcano art, and there is a huge lack of ASCII volcano art on the internet. So if you're looking for a new startup idea, I highly suggest it's a niche market. But as we can see in here, we see that we found our object in here, and we have our dummy attribute user.hacks in there, and we also have our capabilities, which really won't look like much to you. It's just an encoding of the proper capabilities for cap ZUID. We just compiled our shell in here, and we've given this file, this shell right here, the setUID capability so that when it's executed, we are a root user. So, what's interesting here? There's absolutely no memory corruption, not a lot of fancy technique. It's a pretty straightforward exploit, and it just required a little bit of knowledge about the RiserFS file system, a little bit about the extended attributes, and a little bit about Linux capabilities to sort of piece together this exploit, which makes it not really useful for applying to future exploits in most cases, since this isn't really a bug class. It's a one-off exploit. Due to some of these missteps of the logic checking conditions in the RiserFS file system. And this is really representative of a lot of the Linux kernel vulnerabilities that we see. As I said, 60% of them that we saw weren't your traditional memory corruption and were more like this vulnerability. But we also have the standard classes too, which we're going to go through hopefully quickly and chat about. So smashing a stack in the kernel is really no different than smashing a stack in userland. You have a per process kernel stack, which is either 4K or 8K in kernel memory. And we do have existing protection mechanisms built into our compilers, such as stack canaries and bounce checking, which have been applied fairly effectively in user space. But how effective are these same protection mechanisms in kernel space? So one of the things we looked at was the coverage of the fortify source feature of GCC. And fortify source does compile time bounce checking on some of these operations like strcpy or memcopy or sprnf, things that may potentially overflow a static buffer on the kernel stack. And this is actually accomplished through this built-in function called built-in object size, which is a feature of GCC. And if you see here, we've redefined the macro for this built-in object size to return some different values rather than actually doing any sort of verification, just so we can actually count how many times it fails and how many times it succeeds. Built-in object size won't enforce these checkings if it can't get a good idea of what the parameters to these unsafe functions are. If it detects there might be any sort of side effect, it boots out rather than generating potentially incorrect code. So if we do a make yes all yes config, which enables all the kernel options, and run make, we can see that 5,700 times. Do I have those? I have those backwards. Okay, so it actually failed 1,100 times and only succeeded 5,725 times. That's what I get for mocking up fake terminal text there. So the coverage of the fortify source option is actually only 32.9%.